Okay, so if we take a look at the homework, these directions seem pretty intense because it's kind of a tricky one to do, but conceptually it's really not that bad. What we're trying to do is we're trying to trap just these organic vapors inside of this flask. Okay. And if we can trap just the organic vapors in there and then measure their mass, the temperature that they're at, the pressure of the room, and the volume of this flask, then what we can get at is the molecular weight of the organic vapor. Okay. Because the pressure, temperature, and volume are going to allow us to calculate the number of moles. And then we're going to have the mass. We divide the mass by the moles and we get the molecular weight. We've done that in a couple of different ways. Like we just did that with titration, right? By measuring the moles in a different way. So this is actually getting at this formula right here, uh, the ideal gas formula, which is going to be one that we're going to be using a lot in the last couple weeks. So this is kind of like a little preview of that. And basically the number of moles of this gas, if it is ideal, and this is a pretty good situation where it's going to behave like it's ideal, even though it's not, because you're going to have low pressure and high temperature, which is what leads to this being valid. At low temperatures and high pressures, it won't be. So we're going to have the pressure of the room, and that's just given to you in the student data, right? So in the room, there's like a barometer on the wall. I would have just read that off and told people what it was. And then you're going to have the volume of the flask. And the way that we're going to get that is we're going to fill the flask with water, and then we're going to weigh it. And then we're going to subtract the mass of the water in the flask, and we're going to subtract away the flask mass, and that'll give us just the mass of the water, right? So if we know how much the water weighs and we know the temperature of it, we can come down to this guy here and we can get its density, right? So let's think about this a little bit because there's a lot going on here with this thing. And so if we divide by the density, we'll get the volume of the flask. And then the temperature of the water bath is just another measurement that we would have made. So you start with the mass of the empty flask, the foil, and the wire, right? And then you have the mass of the empty flask, the foil, and the wire, and the condensed sample, right? So the condensed sample, this is how much organic vapor. The condensed sample mass is going to be the mass of the organic vapor that we trapped, okay? So obviously, if you take this one and you subtract this one, you're going to get the mass of the organic vapor that got trapped in the flask, okay? And you're going to put that here. The temperature of the water bath is going to be just a measurement that you were given in degrees Celsius. For our math here to work out, we're going to want to convert that to Kelvin. And that's going to be something that's going to come up over and over again when we start doing the gas law problems, is that you typically want to have all your temperatures in Kelvin. We need that absolute temperature. Then you're going to have the barometric pressure in the room. Typically, a lot of times the barometric pressure is read out in millimeters of mercury. You might notice that if like you watch the Weather Channel and stuff a lot. A lot of times in America, it's millimeters of mercury. And that's because old school barometers were literally made with mercury. And you were reading off like the height of a mercury column. We don't do that anymore. It's digital now, but we still kind of use this unit. Internationally, you're going to see pascals used. I've got us converting this to atmospheres. And the reason for that, all of that converting, is if we come up here to the sample, is we have the R factor in that formula I showed you. And the R that I gave you is in liters times atmospheres divided by mole Kelvin. Okay. So when you enter in the pressure and the volume and the temperature, you need to match them up with these units so that they all cancel. All right. Um, if you've done any of this stuff before, you may be aware that you can actually just look up other R values. There are many different, it's all the same number, but they have different units. And if you wanted to do that, you can do that. You know, you could look up one that was millimeters of mercury, milliliters, whatever, and had different units, but you need to be able to cancel them all out. So that's a different way of doing it. But if you're not familiar with that, I suggest you just follow along with what I've done here. Convert this to atmospheres, convert this to liters, and convert this to Kelvin. Plug in your R value. You plug it into the equation here. We'll see atmospheres cancel, liters cancel, Kelvin cancels. You have 1 over moles, which winds up to be moles. And then you can calculate the molecular weight by taking that mass of the condensed sample and dividing it by the moles. Obviously, you usually want that in grams per mole. So there's a little conversion factor I made here because my data was given to me in milligrams. I believe I actually just gave it to you in grams, so you won't need that conversion. So in the end, you'll be able to get the molecular weight here. This section here is about figuring out the volume, right? So you have the mass of the empty flask, you have the mass of the empty flask, and then when it was filled with water, you're going to subtract these, you're going to get the mass of the water. You got the temperature of the water was just given to you in the student data. You're going to look up that density in the table that I gave you up there. You'll divide by that density, and then you're going to get the volume of the flask. And these density values are given to you in grams per milliliter. So this volume will be in milliliters initially, but when you plug it into the ideal gas equation, you want it in liters. So you're going to need to make a conversion there too. After that, let's look at these questions real quick. Using the data collected during the Dumas experiment, calculate the formula mass of the unknown liquid, show all your work. So you're going to do that, right? So we talked about that. So that would be like following through with something similar to sample problem 1. And then we get into the percent mass values and the elemental analysis portion of the lab. And this is the same as some problems that we did before, where you're going to be giving the mass percents of all of the different elements that are inside this compound. You'll assume that you have 100 grams of it. You'll calculate how much mass you have of each one of the elements. You'll divide each one by its atomic mass to find the number of moles. And then you'll divide by the lowest number of moles in order to get the ratios between them. You'll come up with an empirical formula, and then you'll figure out what multiple of that you have that's going to line up with your formula mass that you calculated in the first part. And I did that whole breakdown in sample problem 2, right? So here I'm assuming that I have 100 grams of the sample. This would be like the definition of those mass percents, right? Not as percents, but as a mass fraction. I get all the masses of each one of the different elements. Yours is different than mine. You guys, for instance, don't have chlorine. Then I go through and I divide by each one of the atomic masses. I get the moles of each one. I recognize that this is the smallest number of moles here. I divide each one of the values by the smallest numbers. I get these ratios here. And then I multiply them all by 2 so that I'm close to whole numbers. So this would be like a 2 to 3 to 3 ratio. So that would mean that my empirical formula is C2H3Cl3. And you can see I put that in there right there. So they're a little tricky. Actually, mine is harder than this sample problem's a little harder than even the one that you guys are going to work out. It actually comes out pretty nice for you guys. I don't think you're going to have too much trouble working through it once you get to this part or this part here. Do you guys have any questions about any of that? You want me to go into further depth about any part of it? Sam's shaking her head. Anna Lee, how does Anna Lee feel about it?
Pretty good. You answered any questions I had beforehand, so.
Okay. Okay. Um, it's really, once you figure out what to do with this is actually pretty fast one. It's pretty fast calculations and stuff because you're not having to do like a lot of trials and stuff. And then, so then the last thing that you're going to do is you're going to calculate the percent error based on your formula masses. So you're going to have your experimental formula mass, and then you're going to calculate the formula mass of the molecular formula that you figure out, and you're going to do a percent error for those. And some people were a little confused about where the two would come from, right? So the first one's going to be the one that you based off of the ideal gas law, right? So that's your experimental one. And your theoretical one will be once you determine your molecular formula, you'll go to the periodic table, you'll look up the atomic masses of each one, and then you'll, multiply them out by how many of each kind of atom you have and add them together. That'll be your theoretical one. Okay. But I think I hit all the things that people got a little confused about with this now. If you guys don't have any other questions or anything, or you don't want me to elaborate on anything, we can call it.